If you guys want to look at the problem and happen to have brought your textbooks to class, it is on page 29. It's example 9, a motorcycle ride. Cool. So this is a nice example of accelerated motion and some of the ways that we can talk about accelerated motion and some of the things that we might need to solve for in a problem that has accelerated motion. Okay, so this is going to be a nice, gentle sort of review. Cool? Okay. All right, a motorcycle starting from rest has an acceleration of 2.6 meters per second. After the motorcycle has traveled a distance of 120 meters, it slows down with an acceleration of negative 1.5 meters per second squared until its velocity is 12 meters per second. What is the total distance that this motorcycle has traveled? Okay, so we've got, when we read a problem like this, we should notice that we have two very distinct times of different motion, right? Those are going to be denoted by our two different accelerations. Good? So our first time, we have an acceleration of positive 2.6 meters per second squared. Okay? We know that this distance is 120 meters. Okay? And then, at this point here, our motion changes. Okay? So we're going to have to treat this kind of as two separate parts of our equation. Cool? Because here, all of our equations that we have deal with constant acceleration. And so here we have a constant acceleration, we have a sudden change, and we have another constant acceleration. Good? Okay. All right, so then here we have a speed of acceleration of negative 1.5 meters per second squared. And we have that acceleration till we reach a speed of positive 12 meters per second. Good? Are there any questions? No? You guys get the problem at least? I know this marker is slowly fading, so I'll probably switch to a different side or a different color soon. So it's always a good idea to kind of draw a picture out like this so that you can kind of organize your data, figure out which side goes with which numbers and things like that. The next thing we want to do is look at what the question is. We want to find the total displacement of the motorcycle. So we want to find the distance from here to where we end up going 12 meters per second. Good? Does that make sense? So what we're looking for is our x. Okay? We already know our distance here, right? So we don't need to find a distance for this section. But what about this section here might affect our section here? Any ideas?
Our speed at the end.
Our speed at the end. We're definitely going to need to know our speed here because we need to know how long it's going to take us to get to this speed. So if we don't know our starting speed, then we're not going to be able to find that. So we need to find the velocity here. Okay? Good? So that's one thing we need to find. What do we need to find here to be able to find this distance here? Any ideas? How many meters? We need to find the distance here. So that's another thing we need to find. Okay, so my choice of variables is not necessarily the greatest here because we have our x and x here. A lot of times what physicists do here, just to kind of differentiate, since they're both distances and x stands for a distance, is put a little subscript. So here, that's our total distance. So x sub t is generally our total distance. Good? Any questions on that? Yeah? Okay. So we need to find our velocity here. We need to find our distance here. And then we need to add these two together to get our final distance. Okay? So if you take a problem like this and you give yourself kind of that roadmap of what you need to do, it's a lot harder to just kind of get lost in these problems. Cool? Okay. All right. Any ideas of how we can find our velocity here? Okay, we have an acceleration, so we need to make sure our equation has acceleration in it. We have a distance, okay, so we need to know, we have an equation that has distance in it, okay. Anybody remember an equation like that, or have their book and want to look at their book? We haven't really talked about it, so just wondering if people remember it. No? Okay. One other important part of information, our velocity here, our initial velocity is 0 meters per second. That comes from where it said he started from rest. Forgot to write that off. Cool? All right. For this first part, because we have a distance, the equation we're going to want to use is that big, giant, long one that we learned freshman year. So it's x equals 1/2 times our acceleration times time squared plus v naught times t plus x naught. Okay? This equation is actually going to give us a time. Okay? We don't know our time yet, right? But to actually be able to calculate our velocity from knowing our distance, we need to have a time. Okay? Then we can go back and use the derivative of this equation. We kind of talked about that, right? We can use the v equals at plus v naught equation to actually get our velocity. Cool? Now, we can do these two separately, or we can actually solve this equation for time and put it in here. Okay? Because of the way this works out, it's probably almost equally easy to do either method, just because this is a fairly straightforward equation. Just to give us some practice, I do want to try substituting in this equation into this equation, because that's always a good idea to get used to. Okay? Everybody good? Everybody kind of clear on what we're going to do? Okay. All right. So, like I said, here we don't know t. We want to replace it with things that we know, or things that we want to find. This, we have our final velocity and our initial velocity. We're looking for our final velocity. We know our initial velocity. We know our acceleration. So if we solve this equation for t and put it in here, then we will know all of the things in this equation. Cool? Okay. So to solve this for t, we're going to want to subtract v from both sides. So we get v minus v naught equals at. And then we want to divide both by a. A cancels out here. So we get the useful thing that t equals v minus v naught over a. Good? Okay. Now, when I put this in this equation is going to look really gross. Trust me on this. There's a lot of zeros in here. So it's not near as gross as what you guys think it looks like. Cool? Okay. So we're going to take this. We're going to put it in for t. So we get the equation x equals 1/2 our acceleration times v minus v naught over a squared plus v naught times v minus v naught over a and plus x naught. Okay? So this term specifically right here, probably not one that you're going to have a lot of fun dealing with. But what's zero? V naught is zero. That means that this is just zero. This whole term just disappears because it's multiplied by V naught. We can also call our initial position 0. So that goes away, right? Like I said, a lot of this is 0. So we really don't have to worry about a whole lot. But we kind of, to do this properly, you kind of have to write this out and then say, hey, this is all 0. I can just kind of throw this out for the specific problem. Whereas this whole equation, before we threw stuff out, will work for any case ever. Cool?
How do we know that V naught is 0? So that's V naught.
Yeah, so V naught, this is kind of a crossover of two different variable, I guess, notations. Your initial velocity is your starting velocity. Your V naught is your velocity at time equals 0. So some places will almost always use initial and final. This one is your V final, just so that you have to write less. Your V final doesn't have a subscript. Your initial velocity does. Does that kind of make sense?
Yeah.
Okay, so in this case, these two are exactly the same thing.
And so X naught, is that the same?
X naught is your position at t equals 0. Yep. All right, so if we write this out without all of our 0 stuff, we will get 1/2 a v over a squared. A lot simpler, right? Okay. Because we no longer have the adding in the numerator here, squaring this whole thing just became a lot easier. All we have to do is square the v, square the a, and we're good. Okay? This a will cancel out with one of these a's, so we end up with x equals 1/2 v squared over a. Cool? All right. So now we can actually solve the equation, 4v squared, right? But now this is a lot easier because we got rid of all of our zeros. Okay? Because what we're actually looking for, like we said, is this v here. Everybody good? I don't want to lose people in the middle. Okay. If I'm going too slow, let me know, because I'm used to dealing with the freshmen who don't tell me that they're lost and then panic at the end because they don't know what happened. So, yeah. All right. So we want to solve for v. We're going to multiply both sides by 2 to get rid of the 1/2. We're also going to multiply by a. You guys fine if I do those both at the same time? Okay. I figured you probably would. So we get 2ax equals v squared. So v is the square root of 2ax. And now this is in terms of all of the things that we know, right? We know our acceleration. We know our change in position, or how far we've gone, right? We also know what 2 is. That's just a constant. Cool? All right, so we put our values in now, if we want to. Honestly, we could keep solving like this, but it's probably going to be, we'll do both ways. This marker is now officially not working well. We'll try this. All right, so we get the square root of 2 times our acceleration of 2.6 meters per second times 120 meters. What do we get for that? You guys have your calculators?
I know.
You should bring it to class.
Yeah, I forgot it in math. It wasn't great.
Yeah, that's probably not a good thing. That sounds completely reasonable. My phone calculator is being not helpful.
Yep, that's what I got before. All right.
Don't forget, if you are looking at your units, which is a great way to check things, we would get meters squared over seconds squared, but you have to square root your units as well. So don't forget about that. So we will get 24.98 meters per second, which is good because that's velocity. Everybody good? Are there any questions? All right, so we now know our V here. So we can say V is good. Any questions so far? No? Okay. So we can say we know what it is in variables, we know what it is in numbers. There might be a situation where this will cancel out a whole bunch of stuff. We can try it and see. I'm at the point with the freshmen where when I do something like this, they completely and totally freak out. I'm hoping that you guys are at least at the point where you can see how combining these two equations gave us something way simpler, right? And so a lot of times, if we can do it in variables, it's going to give you a lot easier answer in the long run. Okay? Everybody good? All right. Also, we're not doing this level of things with the freshmen. Yes. So, all right. Now we need to find our distance here. Okay? We are probably going to start with the same equations because we've got a distance, we've got velocity involved, right? Yeah, so we're going to probably start with the same equations. Yeah, we're going to use the exact same equations. All right, can I erase this or are you guys still writing? You guys are good? Okay. All right. Let's see. All right, so this time, we're using the same equations again. This time we have a non-zero initial velocity, because for this section of motion, this is now our initial velocity. This is our V naught. Good? We have a ending velocity that we know. We have an acceleration, and we want to know our distance traveled. Okay, so if we look at our equations, we eventually want to get this, but this time we have all of the information we had here, right? So we have an initial velocity, we have a final velocity, we have an acceleration. We need to find our time, and then we can put it in here, okay? This time, our initial velocity is not zero. That makes our math a little bit more annoying, which is not helpful, okay? All right, so we said this is going to be our initial velocity. So let's try it with variables first, see what happens. So let's actually first, I erased this. We already solved this for t. So let's just go back to our t. Good. And we actually already substituted this in. I just erased it because I wasn't thinking. So we're going to put that back in. Now, we can actually do this in such a way that this x is going to be this. How do you think we can do that? What term allows us to do that, do you think? Because we have this x naught term in there, if we put 120 in there, it's going to give us our total x. You guys see that? Yeah? So this term essentially is saving us that step of calculating this and then adding 120 on at the end. Does that make sense? So if you use these equations properly, you can generally just put it in your calculator once. Cool? Okay. All right, let's try putting this in there. I think some things will cancel out, probably. Although this might be one of those cases where since we know the numbers, it might be easier just to put the numbers in. So once you get to this stage, it is kind of a toss-up as to whether putting variables in will make it any easier. Does that kind of make sense? And you get a feel for that as you solve more equations. It definitely doesn't hurt to put the variables in. A lot of times it's a lot more useful when you have more variables. So like when we did it here, we had a lot of variables that we were looking for, a lot of things canceled out. Here, pretty much everything else is numbers that we would be putting in. So we're not going to get a lot of canceling out. Can you guys kind of see that? Okay. Do you want to try this or do you want to just go straight for numbers? I'll leave it up to you guys. Okay. I would kind of agree with that at this point. So, all right. We get our 1/2. Our acceleration is negative 1.5. Don't forget your negatives. Our
Let's call for the afternoon prayer and announcement. The prayer for generosity. Name of the Father, Son, Holy Spirit. Amen. Lord,
teach me to be generous. Teach me to serve as you deserve. To give and not to count the cost. To fight and not to heed the wounds. To toil and not to seek for rest. To labor and not to ask for reward. Save that of knowing I am doing your will.
Amen. Name of the Father, Son, Holy Spirit. Amen. Drew Everton, David Johnson, dear mind good, come to the guidance and bring your planner. Boys varsity soccer practice will be at the Sportsplex today from 3:30 until 5 o'clock. Ainsley Burnett, please see Mrs. Mims after the bell. Suco shirts are in. Please stay for them and pick up in room 505. They are $17. And a reminder to the freshmen, all freshmen need to report to homeroom after school to receive their Sparkle Light orders. I have another announcement from Coach Hughes. All right, ladies and gentlemen, tomorrow we will have our Halloween costume contest as well as our pumpkin carving contest. Our categories for the costume contest are most creative, funny, dynamic duos, groups, best impersonation, and our best teacher award. That's our teachers dressed up. Pumpkin carving, those pumpkins will go to the library and Mrs. Powderly. If you are entering the costume contest, first of all, everyone is encouraged to dress up, whether you participate in the contest or not. If you are entering the contest, you need to be in the gym between 7:30 and 7:45 a.m. At 7:45 a.m., we will shut those doors and that'll be a firm cutoff for the competition. Make sure that our costumes are appropriate. Please make sure that our mask must be seen and must be visible that you are wearing a mask. Thank you very much.
I will say that if you guys have a calculator that is like a graphing one, or you're typing it in on your computer, problems like this are a little bit easier to deal with. If you have one where your value disappears when you type something in, it does make this problem a little harder. If you have one of those, I would take it by section, maybe like figure out what this is, okay? And then you can substitute that in here and here, and then do this section by itself and write it down. Do this section by itself, write it down. Did you get an answer?
No, I just have a question.
Okay.
So why are you supposed to put meters per second, negative 1.5 meters or what?
Yeah, this should be meters per second squared. Sorry, I forgot units.
Okay.
I got a little too carried away with the problem. Actually, I think that's when announcements started. I'll blame it on announcements. All right. 24.98. Has anybody gotten an answer for this?
I got 280.
280? That's what I got too. So. All right, so once we put all the numbers in, and if we actually look at all of our units, we would actually find that we would get meters out from this equation. Cool? Anybody have any questions on this? No? Do you guys feel fairly comfortable with the layout of how we do these problems? Yeah? Okay. Cool. The bell's about to ring, so I'm going to stop the live stream. That's not the button I wanted. There we go.